So, the most famous equation in human history is completely misunderstood.
Yeah.
Like, if someone put you on the spot right now and asked what E equals mc² actually means, could you answer it?
I mean, I would probably freeze. It's the ultimate intellectual intimidation, right?
Exactly. Or you'd just panic. But don't worry, you are far from alone. I mean, even the actress Cameron Diaz once asked an interviewer in a magazine what the equation really meant.
Oh, really? What did they say?
They both just ended up laughing because neither of them had a clue.
That makes sense. We're sort of culturally conditioned to view that equation as this, like, impenetrable fortress.
Yeah, totally.
We see it and immediately imagine these complex physics diagrams, rocket ships, and, textbooks filled with Greek letters that we have zero hope of understanding.
But in this deep dive, we're throwing out the textbook diagrams. Instead, we're going to look at the biography of the equation.
I love that approach. A biography of the symbol.
Right. We're going to trace the ancestors, the birth, and the adulthood of E, M, C, the equal sign, and the squared symbol.
We really want to understand the actual human stories and the tangible physical mechanics behind those symbols.
Exactly. And to do that, we have to travel back to the birth. Bern, Switzerland, 1905.
Yeah, so when most people picture Albert Einstein, they immediately see the wild white hair, right?
Well, yeah, the eccentric older genius.
Yeah.
The global icon.
Right, but in 1905, Einstein was none of those things. He was 26 years old.
Just a kid, basically.
Yeah, and he was a high school dropout. He had barely passed his university exams, and he only managed that by, cramming with a friend's notes.
Wow.
At this point, he was working as a lowly patent clerk, third class.
His situation was so bleak that his father actually wrote a secret letter to a professor in Leipzig, begging the man to hire his son.
Because Albert felt his career was completely off the tracks.
Yeah, and his father never even got a reply. Think of Einstein in 1905 like a brilliant but totally stuck millennial today.
Oh, that's a perfect way to look at it.
Right. He's working a dead-end admin job just to pay the bills and support a young family. He is literally keeping a quote-unquote department of theoretical physics stuffed inside a single drawer of his office desk.
Just scribbling in secret.
Yeah, he's constantly dodging his strict boss, Dr. Haller, just to sneak a few minutes to write down the ideas that are about to rewrite the rules of the universe.
And, he was completely isolated from the academic establishment, but that isolation is precisely what gave him the freedom to think differently.
Because he didn't know what he wasn't supposed to do.
Exactly. He wasn't sitting in university seminars being told what was impossible by the rigid physics professors of his day. He was free to question the absolute foundations of reality.
So to understand what he was scribbling in that desk drawer, we have to look at the ancestors of the equation, the E and the M.
Right.
Because before Einstein could mathematically link energy and mass, humanity actually had to figure out what those two concepts even were.
And back in the Victorian era, science viewed energy and mass as two completely separate, impenetrable, domed cities.
Like they had absolutely nothing to do with each other.
Nothing at all. So let's look at the first city, E for energy.
Okay, where does that start?
The modern concept of energy really begins with Michael Faraday in the early 1800s. And Faraday was not a formally educated scientist from a wealthy family.
No, he was a boy from a poor London background working as an apprentice bookbinder.
Right. But his job gave him access to books, and he ravenously read the science texts he was supposed to be binding.
That's amazing.
Eventually, he bound his own beautiful book of science notes and sent it to Sir Humphrey Davy, who was the leading scientist of the day.
And Davy was impressed enough to hire him as a lab assistant, right?
It was. It sounds like a fairy tale mentorship,
Except Sir Humphrey Davy later completely betrayed him.
Yeah.
Out of sheer jealousy of Faraday's rising star, Davy actually accused his former assistant of plagiarism.
It's awful. But before that falling out, Faraday made a world-changing breakthrough, and the underlying inspiration for his science came from a very unexpected place.
His religion.
Exactly. He was part of a literalist sect called the Sandemanians. They believed in a sort of circular helping.
Like you help the next person, they help the next, completing a holy circle.
Right. And that religious geometry directly influenced how Faraday approached physics.
How so?
Well, at the time, formally educated scientists were obsessed with finding straight-line forces between electricity and magnetism, like gravity pulling an apple straight to the ground.
But they kept failing.
Right, they kept failing. But Faraday, who didn't have that rigid formal training, imagined invisible circular forces.
So he just pictured it differently.
Yeah, he propped up a magnet, envisioned a whirling tornado of invisible circular lines of force around it, and dangled a wire with an electric current near it.
And because the magnetic force was circular, the dangling wire actually started spinning around the magnet.
Yes, he invented the electric motor right there in his basement.
He proved that electricity and magnetism were deeply linked. But more importantly for our equation, this led to the grand realization that energy is a closed loop. Chemical energy transforms into electrical energy, which transforms into motion, which transforms into heat.
It changes outfits, but the total amount of energy never, ever changes. Energy is conserved.
Okay, so that establishes the concept of energy. But the physical stuff we can touch and hold, matter, or mass, was a completely different story.
Oh, totally. For a long time, scientists genuinely believed physical mass could just vanish.
Which kind of makes sense intuitively. Like if you take a heavy log, burn it in a fireplace, and you're just left with a tiny pile of lightweight ash.
Right. The natural assumption is that the mass of the wood simply ceased to exist.
But that brings us to our second domed city, M-MOM for mass.
And to prove that mass doesn't vanish, we have to jump from a poor London bookbinder to an incredibly wealthy, meticulous French tax accountant.
Antoine Lavoisier.
Yes, in the late 1700s. And Lavoisier was the ultimate precision measurer.
So he and his brilliant wife, Marie-Anne, decided to test this idea of vanishing mass.
Right. They sealed a piece of metal in a glass container, weighed the entire apparatus meticulously, and let the metal rust.
Now, common sense at the time dictated that a rusted, degrading piece of metal would weigh less.
Which is what you'd think.
Yeah, like if I scrape off a layer of rust from an old pipe, the pipe is definitely lighter.
So how does Lavoisier prove that mass doesn't disappear?
Because he weighed the rust itself and the air around it without letting anything escape the sealed glass.
Oh, I see.
He proved that the metal actually gains weight as it rusts. It does this by physically absorbing oxygen out of the air.
Wow.
When Lavoisier weighed the entire sealed container at the end of the experiment, the total weight hadn't changed by a single microgram.
So he proved that matter can move around, it can float as a gas, it can solidify as rust, but it never bursts in or out of existence.
Exactly. The total amount of mass in a closed system is always conserved.
Okay, so we have two separate ledgers, an energy ledger that always balances and a mass ledger that always balances.
But Lavoisier's story has a fascinating dark twist.
Yeah, it really does. The very obsession with meticulous accounting that allowed him to discover the conservation of mass was his tragic downfall. Because he applied his scientific precision to the French tax system.
Right. He actually spearheaded the construction of a massive physical wall around Paris.
Just to stop smugglers and ensure every single cent of tax was collected from the citizens.
And the Parisians absolutely despised this wall. They tore it down with their bare hands right before they stormed the Bastille.
And worse, years earlier, Lavoisier had dismissed an invention from a struggling Swiss doctor.
It was a heat measuring device, right?
Yeah, and that doctor's name was Jean-Paul Marat.
Oh, wow.
Marat later became a ruthless, bloodthirsty leader of the French Revolution. He harbored a bitter grudge over that rejection.
So he used the hated tax wall to whip up the revolutionary mob?
Exactly, and ultimately had Lavoisier sent to the guillotine.
That is just a devastating historical irony. The man who proved mathematically that no speck of mass is ever lost his own head to the revolution.
But his scientific legacy survived. By the dawn of the 20th century, the scientific community accepted these two immutable laws. Energy is conserved, and mass is conserved.
And they were completely separate. Which brings us to the equal sign.
Right.
We take the equal sign for granted, but it was actually invented in 1543 by a mathematician named Robert Ricord.
He used two parallel horizontal lines because, as he put it, no two things can be more equal.
I love that.
Yeah.
But when Einstein puts an equal sign between E and M, he isn't just balancing a checkbook.
No, he's using it as a telescope. He's pointing scientists toward a hidden hiding place for energy that no one had ever thought to look in.
He's claiming that physical mass and intangible energy are actually the exact same thing, just in different states.
But if energy and mass are the same thing, how do you travel between them? Like if there are two domed cities, what is the bridge?
The bridge is the C and the squared symbol.
Exactly. Let's start with C, which stands for Celeritas. It's the Latin word for swiftness. It represents the speed of light.
Now, measuring the speed of light seems impossible without modern technology. Like Galileo actually tried to measure it by having assistants stand on distant hills with lanterns.
Flashing them back and forth, right?
Yeah, trying to time the delay. It was a total failure because light is just way too fast for human reflexes.
It wasn't until a cocky Danish astronomer named Ole Romer came along that we found a mechanism to measure it.
What'd he do?
Well, Romer was tracking Jupiter's moon, Io. He noticed that the timing of Io's eclipses changed depending on where Earth was in its orbit.
Okay, so distance mattered.
Right. When Earth was further away from Jupiter, Io's light took longer to reach us. The delay wasn't because the moon was slowing down, it was because the light itself had to physically cross the extra millions of miles of empty space.
That is so clever.
By measuring that delay, Romer calculated a shockingly accurate speed of light.
Then, James Clerk Maxwell figured out what that light actually is mechanically. He realized it is an electromagnetic wave.
It's a wave of electricity leapfrogging over a wave of magnetism, jumping forward over and over again through space.
And this brings us right back to our 26-year-old patent clerk, Einstein. He realized something profound about this leapfrogging wave.
You cannot catch up to it.
Right.
Einstein recognized that the speed of light is the absolute speed limit of the universe. It is a physical boundary, much like absolute zero is the boundary for temperature.
You cannot go faster than light no matter how hard you try.
Exactly.
Let me try to visualize this because it defies everyday logic. Like imagine you are in a space shuttle blasting through the vacuum of space.
Okay, I'm picturing it.
You keep pumping fuel into the engines, thrusting forward, going faster and faster. But what happens when you get right up to the edge of the speed of light?
Right, because the engines are still firing.
Yeah, you are still pumping massive amounts of energy into the system. So, if the universe physically will not allow the shuttle to accelerate any further, where does all that thrust energy actually go?
That is the pivotal question. The energy cannot just disappear. Faraday proved that.
Exactly.
Because the shuttle cannot accelerate past the speed limit, its inertia begins to increase. It begins to resist the acceleration.
So the energy has to change form.
Yes. The sheer energy of those engines is physically forced to change state. It gets squeezed into mass.
Wait, really?
Yeah. To an outside observer, as the shuttle pushes against the speed of light, it literally swells up. It becomes physically heavier. The energy transforms into mass.
That is mind-bending. And the conversion factor dictating that precise transformation is c, the speed of light.
Right, but it's not just c. The equation is E equals mc². We have to understand the squared symbol.
And to do that, we look at one of the most incredible figures in this entire narrative, Émilie du Châtelet.
She was an 18th century French physicist who completely defied the gender roles of her era.
She hid from suitors, she literally dueled men with swords, and she turned her husband's abandoned chateau into a massive, world-class research laboratory.
Alongside her lover, the famous philosopher Voltaire.
What a life.
Incredible, right? And du Châtelet was attempting to solve a major dispute in physics. Isaac Newton, whom almost everyone followed, believed that energy simply equaled mass times velocity.
But a rival thinker, Gottfried Leibniz, suspected energy scaled differently.
Yes. So du Châtelet designed a brilliant physical experiment to settle the debate. She used an apparatus built by Wilhelm to drop brass spheres into a bed of soft clay.
I can see how this works. The depth of the dent in the clay give you a visual, physical measurement of the sphere's kinetic energy.
Exactly.
If Newton was right, dropping a sphere going twice as fast should make a dent twice as deep.
Right. But that is not what happened.
What happened?
When she dropped a sphere going twice as fast, it didn't sink twice as deep. It sank 4 times as deep.
Oh, wow.
When it went 3 times as fast, it sank 9 times as deep. She proved experimentally that energy does not scale directly with speed. It scales with the square of the velocity.
So bringing this back to Einstein's desk drawer, what does that squared symbol actually mean for the equation?
It means the conversion factor between a piece of solid mass and pure energy is the speed of light squared.
And the speed of light is already an astronomically huge number, like 670 million miles per hour.
Right. When you square that number, you get 448 quadrillion, 900 trillion.
Good Lord.
It is an unfathomably massive multiplier. It means that an impossibly tiny speck of physical mass contains an explosively huge amount of trapped energy.
That is staggering. But you know, it's one thing to have a neat mathematical equation that says solid matter hides massive energy.
It's a completely different challenge to actually extract that energy.
Exactly. To do that, scientists had to literally crack open solid matter. They had to figure out how to open the atom.
And the first clue came from Marie Curie.
Right.
She was studying radium, which mysteriously glowed and poured out intense energy for thousands of years.
But remarkably, it did this without any measurable loss of physical mass.
Tragically, working so closely with this radiation eventually gave her fatal leukemia, but she proved that seemingly dead matter was actively doing something.
And later, Ernest Rutherford discovered the actual physical architecture of the atom.
Which was bizarre. To picture just how weird Rutherford's discovery was, imagine dropping a massive meteor into the Atlantic Ocean. But instead of splashing into the water, the meteor falls through completely empty space all the way to the sea floor.
Right.
Down there, it hits a tiny, incredibly dense device that repels it, shooting the meteor right back up into the sky.
That's a great analogy. Rutherford proved that atoms are not solid balls. They are almost entirely empty space, with a microscopic, dense, positively charged nucleus at the dead center.
But that tiny nucleus was tightly locked. To unleash the energy inside, scientists needed a key.
And James Chadwick provided the first half of that key by discovering the neutron.
A neutral particle that lives inside the nucleus alongside the protons.
And he incredibly did some of this foundational research using radioactive toothpaste while he was a prisoner of war in Germany.
Radioactive toothpaste, you really cannot make that up.
No. But even with the neutron discovered, the physicists had a mechanical problem.
Right, because they were firing these newly discovered neutrons at target atoms like tiny bullets, hoping to split the nucleus.
But the neutrons were moving so fast that they just zipped right through the empty space of the atom.
It was Enrico Fermi in Rome who figured out how to make the key fit the lock.
And what did she do?
He used buckets of water from a goldfish pond to slow the neutrons down.
Buckets of water from a goldfish pond.
Yes. And the mechanism for why slowing them down works is fascinating. It all comes down to wave-particle duality.
Okay, explain that.
A fast-moving neutron acts like a streamlined physical bullet. It shoots straight through the empty space.
Right.
But if you slow that neutron down, its wave nature becomes more pronounced. It begins to act less like a bullet and more like a spread-out wave.
It gets wider.
It becomes wider and, in a sense, sticky. Because it is moving slowly and is more dispersed, it has a drastically higher chance of snagging on the dense target nucleus and slipping inside.
So, Fermi found the sticky key. But turning that lock and unleashing the terrifying energy of E equals mc² took a brilliant woman who was shivering in the Swedish snow.
Lise Meitner.
Yeah, she was an Austrian Jewish physicist who had worked in Berlin for decades with her research partner, Otto Hahn.
But when the Nazis took power, Hahn betrayed her.
He threw her to the wolves to preserve his own career and laboratory, forcing her to flee to Sweden with absolutely nothing.
It was a profound personal and professional betrayal. Yet, despite being exiled, she continued to guide the research through letters.
Which is incredible dedication.
It really is.
Yeah.
In December 1938, she was walking in a snowy Swedish forest with her nephew, Robert Frisch.
Right.
Hahn had mailed her a laboratory result he couldn't comprehend. When he bombarded uranium with slow neutrons, he found barium left behind in the sample.
And I completely understand why Hahn was confused. Uranium is a massive, heavy element. Barium is roughly half its size.
Right.
Hahn assumed that hitting a nucleus was like hitting a boulder with a hammer. You could only chip off tiny pieces.
Or?
He couldn't grasp how a uranium atom had left behind something half its size.
So Meitner and her nephew stop by a tree trunk in the snow. They sit down and start sketching.
Okay.
They visualize the nucleus not as a solid rock, but as a dynamic liquid drop.
Oh, that makes sense.
Meitner realizes the mechanism. When that slow, sticky neutron enters the already overstuffed uranium drop, it adds just enough extra energy to make the drop wobble violently.
The surface tension gives way.
Exactly. It stretches, bulges at the ends, and finally, it snaps perfectly in half.
And this is the exact moment the math on the chalkboard becomes physical reality. Meitner, standing in the freezing cold, calculates the mass of the two new halves in her head.
In her head?
Yes. She realizes that the two halves, when added together, weigh slightly less than the original uranium drop. Exactly 1/5 of a single proton's mass had disappeared.
And the mass does not just vanish.
Right. It crosses Robert Record's equal sign.
It gets multiplied by Émilie de Châtelet's speed of light squared. And because that multiplier is so astronomically huge, that missing fraction of a microscopic proton violently erupts as 200 million electron volts of pure energy.
Nuclear fission is born right there in the snow.
And the implication of that calculation is instantly terrifying.
Because it's 1939.
Right.
The world is rapidly plunging into the most destructive war in human history. And now, the scientific community suddenly knows that an ultimate weapon of unparalleled destruction is theoretically possible.
A desperate global race begins, and the Germans had a massive head start.
Yeah, Einstein actually signed a warning letter to President Franklin D. Roosevelt about the danger, but it was intercepted by an archaic American bureaucrat named Lyman J. Briggs.
Who literally locked the British intelligence reports in his safe and did nothing.
Unbelievable. Meanwhile, the Nazis aggressively recruited Werner Heisenberg to lead their nuclear program.
And Heisenberg only survived the brutal SS purges because his mother personally went to Heinrich Himmler's mother to ask for a favor.
The historical coincidences are just staggering. Heisenberg gets to work building a virus house reactor.
Heisenberg's reactor design relied on using flat sheets of uranium and heavy water to slow down the neutrons and create a chain reaction.
Okay.
While Germany pushed forward, the Americans finally woke up and created the Manhattan Project.
This project required an unprecedented coordination of science and military logistics. And it really highlighted a sharp contrast in leadership styles.
Oh, definitely.
You had Ernest Lawrence, representing blunt, brute force American engineering, building uranium enrichment factories a mile long.
And then you had J. Robert Oppenheimer, appointed to lead the highly secret bomb design lab at Los Alamos.
Which on paper looked like a catastrophic personnel decision.
Right, because Oppenheimer was notoriously insecure and highly strong.
Yeah. In his youth, he suffered a psychological breakdown and actually tried to strangle a friend.
Oh, wow.
And as a university teacher, he was so detached from reality that he assigned his students textbooks written in Dutch.
So why would the military put a fragile theoretician in charge of the most vital engineering project of the war?
Exactly. Why him?
Because that exact psychological fragility made him the perfect manager for a secluded laboratory filled with eccentric, brilliant, and highly sensitive prima donnas.
Oh, I see.
Oppenheimer intimately understood insecurity. He knew exactly how to handle massive egos like Edward Teller.
That makes a lot of sense.
He won over the rebellious Richard Feynman by securing a special train pass so Feynman could regularly visit his dying wife.
Oppenheimer's emotional intelligence and empathy were the glue that held the massive egos of the project together.
And they needed every ounce of that collaboration to solve their biggest mechanical hurdle implosion.
Right. They had manufactured a new fuel, plutonium. But if you just shot two pieces of plutonium together like a gun, it blew itself apart before a true nuclear chain reaction could ignite.
So Oppenheimer's team realized they had to wrap a solid sphere of plutonium in high explosives and detonate them simultaneously.
To crumple the sphere inward perfectly.
The implosion physics were incredibly complex. They had to figure out how to compress the core while simultaneously bouncing escaping neutrons back into the center to keep the reaction going.
And to study neutron reflection, they needed a material with a highly dense atomic structure that would bounce the neutrons back without absorbing them.
So they literally requested a solid gold sphere from Fort Knox.
Because gold nuclei are incredibly dense, they act as perfect mirrors for neutrons.
That priceless gold sphere just sat on a desk in the Los Alamos library like an ordinary paperweight.
That's wild.
Yeah.
But while the Americans were calculating implosion in the desert, the terrifying reality was that Heisenberg was making real progress in Germany.
The Allies knew they had to sabotage the German effort.
And the absolute weak link in Heisenberg's plan was the heavy water being produced at the Vemork plant in occupied Norway.
Right. Without that heavy water to slow the neutrons down, Heisenberg's reactor couldn't ignite a chain reaction.
The attempts to destroy that heavy water supply were heartbreaking.
They really were. The British initially sent highly trained glider troops, but the gliders crashed in the brutal mountains.
And every single survivor of the crash was captured and executed by the Gestapo.
It ultimately fell to a tiny group of just 9 Norwegian resistance fighters.
Their mission is just unbelievable. They ski across a frozen, seemingly impassable gorge in the dead of winter. They use heavy bolt cutters on the perimeter gates, crawl through a tiny cable duct to bypass the guards, and blow up the heavy water cells, sending the crucial water straight down the facility's drains.
It was a tactical masterpiece, but incredibly, the Germans rebuilt the facility.
We did.
Eventually, the Nazi command decided to move the remaining heavy water supply back to Germany via a civilian ferry across Lake Tinzhou.
And the Norwegian resistance faced an agonizing, excruciating moral trade-off.
Right. To stop the Nazi atomic bomb from becoming a reality, they had to sink the ferry.
But sinking the ferry meant knowingly killing their own innocent countrymen who were passengers on board.
They made the horrific choice, sank the ferry, and effectively starved the German atomic program of its essential resource.
Man, let's step back for a second, look at the sheer scope of what we just covered.
He's massive.
We have followed an incredible, sprawling journey. A simple, elegant equation scribbled in a wooden desk drawer by an isolated 26-year-old patent clerk in Switzerland.
And that tiny string of mathematical symbols ended up connecting the life struggles of a poor London bookbinder discovering circular forces.
A meticulous French accountant sent to the guillotine.
And an exiled female physicist shivering in the Swedish snow calculating missing mass.
All of it leading to a desperate, tragic commando raid on a frozen Norwegian lake to stop a world-ending weapon.
You are listening to this right now, and it feels like a grand historical thriller.
It really does.
But it is so much more profound than that. Because the equation Einstein wrote down isn't just about the history of human warfare or atomic bombs. It is the fundamental operating code of the physical universe itself.
I want to leave you with this one final thought to mull over. We spent a lot of time talking about the bomb.
Right.
But the exact same mathematical mechanic that powers an atomic weapon, taking a microscopic fraction of physical mass, squeezing it completely out of existence, and unleashing a roaring, violent explosion of energy.
That is the exact same process happening right now, constantly, inside the core of every star in the sky.
Exactly. You are alive today, listening to this deep dive, breathing the air. Because E equals mc² is quietly, continuously burning away the physical mass of our sun, transforming that missing matter into the light and the warmth that makes absolutely all life on Earth possible.